Hi guys, this is Zulekha from Edureka, and I welcome you to today's session on support vector machines. SVM or support vector machine is one of the most effective machine learning classifier, and it has been used in various fields such as face recognition, cancer classification, and so on. Today's session is dedicated to how SVM works, the various features of SVM, and how it is used in the real world. So without any further ado, let's take a look at the agenda for today. We're going to begin the session with an introduction to machine learning and the different types of machine learning. Next, we'll discuss what exactly support vector machines are, and then we'll move on and see how SVM works and how it can be used to classify linearly separable data. We'll also briefly discuss about how nonlinear SVMs work, and then we'll move on and look at the use case of SVM in colon cancer classification. And finally, we'll end the session by running a demo where we'll use SVM to predict whether a patient is suffering from a heart disease or not. Okay, so that was the agenda. Let's get started with our first topic. So what is machine learning? Machine learning is a science of getting computers to act by feeding them data and letting them learn a few tricks on their own. Okay, we're not going to explicitly program the machine. Instead, we're going to feed it data and let it learn. The key to machine learning is the data. Machines learn just like us humans. We humans need to collect information and data to learn. Similarly, machines must also be fed data in order to learn and make decisions. So let's say that you want a machine to predict the value of a stock. Alright? In such situations, you just feed the machine with relevant data, after which you develop a model which is used to predict the value of the stock. Now, one thing to keep in mind is the more data you feed the machine, the better it'll learn and make more accurate predictions. Obviously, machine learning is not so simple. In order for a machine to analyze and get useful insights from data, it must process and study the data by running different algorithms on it. Alright? And today we'll be discussing about one of the most widely used algorithms called the support vector machine. Okay, now that you have a brief idea about what machine learning is, let's look at the different ways in which machines learn. First, we have supervised learning. In this type of learning, the machine learns under guidance. Alright, that's why it's called supervised learning. Now at school, our teachers guided us and taught us. Similarly, in supervised learning, machines learn by feeding them labeled data and explicitly telling them, hey, this is the input and this is how the output must look. Okay, so guys, the teacher in this case is the training data. Next, we have unsupervised learning. Here the data is not labeled and there is no guide of any sort. Okay, the machine must figure out the data set given and must find hidden patterns in order to make predictions about the output. An example of unsupervised learning is an adult like you and me. We don't need a guide to help us with our daily activities. We figure things out on our own without any supervision. Alright, that's exactly how unsupervised learning works. Finally, we have reinforcement learning. Let's say you were dropped off at an isolated island. What would you do? Now, initially, you'd panic and you'd be unsure of what to do, where to get food from, how to live, and all of that. But after a while, you will have to adapt. You must learn how to live in the island, adapt to the changing climate, learn what to eat and what not to eat. You're basically following the hit and trial concept because you're new to this surrounding and the only way to learn is experience and then learn from your experience. This is exactly what reinforcement learning is. It is a learning method wherein an agent interacts with its environment by producing actions and discovers errors or rewards. Alright, and once it gets trained, it gets ready to predict the new data presented to it. Now, in our case, the agent was you, basically stuck on the island, and the environment was the island. Alright, okay, now let's move on and see what SVM algorithm is all about. So guys, SVM or support vector machine is a supervised learning algorithm which is mainly used to classify data into different classes. Now, unlike most algorithms, SVM makes use of a hyperplane which acts like a decision boundary between the various classes. In general, SVM can be used to generate multiple separating hyperplanes so that the data is divided into segments. Okay, and each of these segments will contain only one kind of data. It's mainly used for classification purpose wherein you want to classify a data into two different segments depending on the features of the data. Now, before moving any further, let's discuss a few features of SVM. Like I mentioned earlier, SVM is a supervised learning algorithm. This means that SVM trains on a set of labeled data. SVM studies the label training data and then classifies any new input data depending on what it learned in the training phase. A main advantage of support vector machine is that it can be used for both classification and regression problems. Alright. Now, even though SVM is mainly known for classification, the SVR, which is the support vector regressor, is used for regression problems. Alright, so SVM can be used both for classification and for regression. Now, this is one of the reasons why a lot of people prefer SVM, because it's a very good classifier, and along with that, it is also used for regression. Okay. Another feature is the SVM kernel functions. SVM can be used for classifying non-linear data by using the kernel trick. The kernel trick basically means to transform your data into another dimension so that you can easily draw a hyperplane between the different classes of the data. Alright, non-linear data is basically data which cannot be separated with a straight line. Alright, so SVM can even be used on non-linear data sets. You just have to use the kernel functions to do this. Alright, so guys, I hope you all are clear with the basic concepts of SVM. Now let's move on and look at how SVM works. So guys, in order to understand how SVM works, let's consider a small scenario. Now for a second, pretend that you own a farm. Okay, and let's say that you have a problem and you want to set up a fence to protect your rabbits from the pack of wolves. Okay, but where do you build your fence? One way to get around the problem is to build a classifier based on the position of the rabbits and wolves in your pasture. So what I'm telling you is you can classify the group of rabbits as one group and draw a decision boundary between the rabbits and the wolf. Alright. So if I do that and if I try to draw a decision boundary between the rabbits and the wolves, it looks something like this. Okay. Now you can clearly build a fence along this line. In simple terms, this is exactly how SVM works. It draws a decision boundary, which is a hyperplane between any two classes in order to separate them or classify them. Now I know you're thinking, how do you know where to draw a hyperplane? The basic principle behind SVM is to draw a hyperplane that best separates the two classes. In our case, the two classes are the rabbits and the wolves. So you start off by drawing a random hyperplane and then you check the distance between the hyperplane and the closest data points from each class. These closest or nearest data points to the hyperplane are known as support vectors. And that's where the name comes from, support vector machine. So basically the hyperplane is drawn based on these support vectors. So guys, an optimum hyperplane will have a maximum distance from each of these support vectors. Alright. So basically the hyperplane which has the maximum distance from the support vectors is the most optimum hyperplane. And this distance between the hyperplane and the support vectors is known as the margin. Alright. So to sum it up, SVM is used to classify data by using a hyperplane such that the distance between the hyperplane and the support vectors is maximum. So basically your margin has to be maximum. Alright. That way you know that you're actually separating your classes. Alright. Because the distance between the two classes is maximum. Okay. Now let's try to solve a problem. Okay. So let's say that I input a new data point. Okay. This is the new data point. And now I want to draw a hyperplane such that it best separates the two classes. Okay. So I start off by drawing a hyperplane like this. And then I check the distance between the hyperplane and the support vectors. Okay, so I'm trying to check if the margin is maximum for this hyperplane. But what if I draw a hyperplane which is like this? Alright, now I'm going to check the support vectors over here. Then I'm going to check the distance from the support vectors. And for this hyperplane, it's clear that the margin is more. Alright, when you compare the margin of the previous one to this hyperplane, it is more. So the reason why I'm choosing this hyperplane is because the distance between the support vectors and the hyperplane is maximum in this scenario. Okay. So guys, this is how you choose a hyperplane. You basically have to make sure that the hyperplane has a maximum margin. Alright. It has to best separate the two classes. Alright. Okay. So far it was quite easy. Our data was linearly separable, which means that you could draw a straight line to separate the two classes. Alright. But what will you do if the data set is like this? You possibly can't draw a hyperplane like this. Alright. It doesn't separate the two classes at all. So what do you do in such situations? Now, earlier in the session, I mentioned how a kernel can be used to transform data into another dimension that has a clear dividing margin between the classes of data. Alright. So kernel functions offer the user this option of transforming non-linear spaces into linear ones. Non-linear data set is the one that you can't separate using a straight line. All right. In order to deal with such data sets, you're going to transform them into linear data sets and then use SVM on them. Okay, so a simple trick would be to transform the two variables x and y into a new feature space involving a new variable called z. All right. So guys, so far we were plotting our data on two-dimensional space, correct? We were only using the x and the y axis. So we had only those two variables, x and y. Now, in order to deal with this kind of data, a simple trick would be to transform the two variables x and y into a new feature space involving a new variable called z. Okay, so we're basically visualizing the data on a three-dimensional space. Now, when you transform the 2D space into a 3D space, you can clearly see a dividing margin between the two classes of data. All right, now you can go ahead and separate the two classes by drawing the best hyperplane between them. Okay, that's exactly what we discussed in the previous slides. So guys, why don't you try this yourself? Try drawing a hyperplane which is the most optimum for these two classes. All right. So guys, I hope you have a good understanding about nonlinear SVMs. Now let's look at a real world use case of support vector machines. So guys, SVM as a classifier has been used in cancer classification since the early 2000s. So there was an experiment held by a group of professionals who applied SVM in a colon cancer tissue classification. So the dataset consisted of about 2000 transmembrane protein samples, and only about 50 to 200 gene samples were input into the SVM classifier. Now this sample which was input into the SVM classifier had both colon cancer tissue samples and normal colon tissue samples. Alright. Now the main objective of the study was to classify gene samples based on whether they are cancerous or not. Okay, so SVM was trained using the 50 to 200 samples in order to discriminate between non-tumor from tumor specimens. So the performance of the SVM classifier was very accurate for even a small data set. Alright, we had only 50 to 200 samples, and even for the small data set, SVM was pretty accurate with its results. Not only that, its performance was compared to other classification algorithms like naive Bayes, and in each case, SVM outperformed naive Bayes. So after this experiment, it was clear that SVM classified the data more effectively and it worked exceptionally good with small data sets. Alright, now let's get into the practical part. We'll run a demo to better understand how SVM can be used as a classifier. Okay, so guys, before we run the demo, let's look at our problem statement. So our problem statement is to study a heart disease data set and build a classifier to predict whether a patient is suffering from heart disease or not. Alright. Now this data set will have n number of patients along with details about the patients. Okay. For example, their age, the cholesterol level, their sex, all that will be mentioned in the data set. So we're basically going to study this data set, build a SVM classifier, and then predict whether a patient is suffering from any heart disease or not. Alright. So we're creating two classes over here. One class consists of patients suffering from heart disease, and the other class is the lucky one, which is not suffering from any sort of heart disease. Alright, so let's move on and look at today's demo. So guys, in order to save some time, I've already typed out the code, but don't worry, I'm going to explain each and every line of code over here. Alright, now guys, in our demo, we'll be using the carrot package. Alright, the carrot package, which is also known as a classification and regression training. It has tons of functions which can help us to build predictive models. So it contains tools for data splitting, pre-processing, feature selection, tuning, supervised and unsupervised learning algorithm. Okay, so to use it, we first need to install it using this command, install.packages carrot. Alright, the carrot package is very helpful because it provides us direct access to various functions. So for training our model, we require algorithms like KNN, SVM, decision tree, linear regression. All of these algorithms are already pre-coded in the carrot package. Okay, so after installing it, we just need to load the package into our console. To do that, we have this code snippet which says library and the name of the package. Okay, so our next step is to load the data set. So guys, for this demo, we'll be using a heart disease data set which consists of various attributes like the person's age, sex, cholesterol level, and etc. In the same data set, we'll have a target variable which is used to predict whether a patient is suffering from any heart disease or not. Okay, I'll show you the target variable in a bit. Okay, so this is the aim of our demo. We're going to use the SVM to classify whether a person is going to be prone to a heart disease or not. Okay, now let's load the data. Okay, before I do that, let me just show you the data set. So you can see that it has around 14 attributes, okay, till column n, and the last attribute over here, the n column, is the target variable. Okay, we'll be predicting this using our SVM model. Okay, so guys, I already have the data set. Now all I have to do is I need R to read the data set from my machine. Okay, so to do that, we have this line of code. So what I'm doing here is, this is the name of my data set, heart_dataset.csv. Okay, it's stored in a CSV or a comma separated file. All right, now the location of this data set is over here, user Zulekha desktop. Okay, this is basically the path to my data set. After that, there is another field called separator. Okay, this just identifies that this is a comma separated file. And lastly, we have another parameter which says header. Header indicates whether my data set has a header or not. Okay, in this case, it's false. All right. So guys, I'm basically using this read.csv function to read my data set. All right, and I'm storing the data set in a variable called heart. Now let's run this line of code. Run both of these lines first. Okay. Now let me run this line of code. Okay. All right, now that we've imported our data set, let's check the structure of our data set. Okay, so you use this function called str to check the structure of your data set. So it basically has 14 attributes, and it shows us that there are 300 observations and 14 variables over here. Okay, so guys, all of these values are converted into numerical format. So that's why you might not be able to understand this data set. But in order for R to run this data set, it has to be in numerical form. For us to perform any computation on the data set, it has to be in numeric form. All right. Okay, then if you want to display the first 5-6 rows of your data set, you can use the head function. All right, this head function will display the first 5-6 observations of your data set. All right, so this is what our data set looks like. These are all the attributes. Okay, there are 14 attributes, and this is our target variable that we're going to predict. All right, now our next step is to split the data into training set and the testing set. Okay, now this process is also called as data splicing. Okay, so we're going to use the training set specifically for our model building and the testing set for evaluating the model. All right, so this entire set of code is basically for splitting the data. Okay, now here you can see this create data partition function. So the caret package provides a method called the create data partition, which is basically for partitioning our data into training and testing set. Okay, here you can see that to this function, I've passed 3 parameters, y, p, and list. Now the y parameter takes the target variable into consideration. Okay, so it checks that within my heart data set, v14, which is my target variable. All right, our next parameter p basically holds a decimal value. Now p basically stores a decimal value from 0 to 1. Okay, so between 0 and 1, it has a value, and over here you can see that 0.7 is a value for p. It means that we're splitting our data in the ratio 70:30. Okay, so 70% of our data is going to be used for training, and the remaining 30% will be used for testing the model. Okay, so I'm storing this in the train variable. Okay, then I'm assigning a new variable called training, which contains my 70% of the data, and the remaining, that's why it says minus train, which is the remaining data set, which is the 30% of the data, is assigned to the testing variable. All right, so let's run the set of code. Next, for checking the dimensions of our training data frame and the testing data frame, we can use this dimension function. Okay, dim. Okay, let's look at the output. So the training data set has 210 observations with 14 variables, obviously 14 attributes, and 90 observations are present in the testing data set. All right. Okay, now our next step is to clean the data. So if there are any missing values or inconsistent values, they have to be dealt with before we build the training model. Okay, so here we're using the any NA function, this function, which checks for any null values or any non-available values. Okay, so let's run this. All right, on running this, we get the return value as false. Okay, here you can see that it says false. Okay, this means that there are no missing values in our data set and we're good to go. All right, now let's finally check the summary of our data set to see if everything is correct. Okay, now the output here shows that the values of various variables are not standardized. Okay, for example, consider this v14 variable. Okay, this is our target variable and it holds only two values, either it holds 0 or it has 1. Okay, instead this should be a categorical variable. Okay, to convert these to categorical variables, we need to factorize them. All right, so let's factorize the variable v14. Okay, now this line over here, it basically converts the training data frame v14 column to a factor variable. Okay, so this v14 variable, it will turn it into a factor variable. So let's run this. All right, now our next step is to train our model. So before we train our model, we'll first implement the train control method. Okay, here you can see the train control method. Now this will control all the computational overheads so that we can use the train function provided by the caret package. All right, here you can see in the next line, I've used the train function. Now caret package provides this function in order to train different algorithms. Now guys, this train method is offered by the caret package itself. You can use it to train the data on different algorithms. Okay, all right, so first let's focus on the train control method. Okay, this method, train control method here is taking three parameters. Okay, it has a method attribute, number and repeats. Now the method parameter defines the resampling method, and in this demo we'll be using the repeated CV or the repeated cross validation method. The next parameter is the number parameter. This basically holds a number of resampling iterations. Okay, so how many iterations you want to do on this data set, that is the number that this is going to represent. Okay, the repeats parameter contains the sets to compute for our repeated cross validation. So here we're setting the number equal to 10 and the repeats equal to 3. All right, this train control method will return a list to us, all right, which is basically going to be stored in this, and we're going to pass this to our training method. This is the train method. All right, so let's run this line of code. Okay, so we've run that successfully. So now we have the train function. Okay, now this function has to be passed with the method parameter set to SVM linear. Okay, we are passing our target variable as well, which is v14, and this dot and this approximation basically indicates that our model is using all the attributes in our classifier, and v14 is the target variable. Okay, it's indicating that v14 is our target variable and it's using all the attributes in the data set. Next, we have the TR control parameter. Okay, this TR control parameter should be passed with the results from our train control method. Okay, so whatever we ran in the train control method was stored in this variable. Okay, so we're going to pass that variable over here. Next is the pre-processing parameter. This is for pre-processing our training data set. All right, and these two, center and scale, help for centering and scaling the data. Okay, and then we also have the tune length parameter. This parameter holds an integer value. Okay, this is for tuning our algorithm. So let's run this block of code. All right, now you can check the result of our train method. Okay, it's stored in this variable. So let's run this variable. Okay, so it says support vector machine with linear kernel. This means that our data was linearly separable, and that's why we use the linear kernel over here. Now here is just showing us the pre-processing results, resampling results, and our sample sizes. All right, and here C value was held at 1 because this is a linearly separable model. Now since our model is trained with C value as 1, we are ready to predict classes for our test set. Okay, we can use the predict method. This is the predict method. Now this method is provided by the caret package itself, and we are going to pass two arguments to this method. The first parameter is our trained model. Okay, what we just trained, SVM linear. We're going to pass that, and the second parameter, which is new data, it basically holds our testing data frame. We created this testing variable at the beginning of a session. Okay, here is the testing variable. We created it to store our testing data. All right, so we're basically going to pass the testing data frame and our trained model. Okay, so let's run this. All right, it's run successfully. So if I run our testing model, this one, you get the prediction values. Okay, so 0 stands for patients who have nothing to do with a heart attack, and 1 is basically patients suffering from heart diseases. Okay, so it's showing this for each and every patient. So the 0 value represents the first patient, the 1 value represents the second one, third one, fourth one, and so on. Okay. So guys, this was our prediction. Now let's also test the accuracy of our model. Okay, we're going to use the confusion matrix to predict the accuracy. All right. Let's run this line of code. Okay, the output shows that our model's accuracy for test set is 86.67%. Okay, basically 0.866, which stands for 86.67%. Now, in order to improve the performance of our model, we can customize the cost value in our linear classification. Okay, so in order to do this, you're just going to input values into grid search. Okay, this is our grid variable, and we're going to input values for C in order to improve the performance of our model. Okay, so we're going to put some C values using the expand.grid method. And our next step is to use this data frame for testing our classifier at specific values of C. Okay, so we've assigned some specific values of C. All right, so let's just run this line of code. Now we're again training our model using these C values. All right, so let's run this. So guys, the explanation to this was already told before. So this is the same line of code that we ran earlier. Now, if you want to view the model, just run this line. All right, so now it's saying that for C value as 0.05, our accuracy was the most. Okay, so this is where it's showing the accuracy. All right, so 0.82. So guys, 0.82 or 82% is quite accurate because we're not actually feeding a lot of data into the SVM classifier. Okay, so this basically returns the accuracy level for each value of C. Okay, for all the values of C, it's going to return an accuracy level over here. Okay, now you can also plot this and try to summarize it if you want. So let's run this plot. All right. So you can see that for around 0.4 or 0.5, I'm not sure, the accuracy is the maximum. Okay, this is the cost value and this is the accuracy value. All right. So now you know for what value of C you'll have to build your model. So guys, this was a very easy way to test the accuracy of the model and to check for which value of C our model is the most accurate. So now we finished training our model with these C values. Now let's test the model for the same C values. Okay, if you want, you can do this. So I'm running the same lines of code that I ran earlier. Okay. So to the predict function, I'm basically passing our training model and the testing data set. Okay. Then I'm just showing you the output of our testing model. All right. So 0 basically shows that a patient is not suffering from heart disease, and 1 shows that a patient is suffering from heart disease. All right. So these were the predictions that we made. You can also again go and check the accuracy. Since we created a new testing model over here with different C values, we can also check the accuracy of this model. Okay, so I'm passing the name of this model over here and I'm testing our accuracy of the prediction variable V14. All right, let's run this confusion matrix and hopefully this gives us a higher accuracy rate. Okay, it actually gives us a higher accuracy rate. Earlier we got 0.86 something. Now it is 87%, 0.8778. Okay, which is obviously more than 0.86. So guys, this is how you improve the accuracy of your matrix. You tune and play around with the value of C, and then you find out for which value of C our model will be more accurate. Okay. So guys, this was a simple demonstration of how SVM can be used to predict whether a patient has a heart disease or not. Okay, and it was quite good because it is 87% accurate, which is a good enough number, correct? All right. So let me just summarize what we did in the demo. Okay, so we basically studied a data set which contained many patients with information such as their age, cholesterol level, their sex, and etc. Okay, we studied these different attributes of each patient to predict whether a patient will suffer from a heart disease or he will not. And we used the linear SVM algorithm to do this. Okay, and in the end, we built a model with an accuracy of 87.78 accuracy rate, which is pretty good. So guys, give yourself a pat on the back because now you've successfully run a demo which shows how SVM is a very accurate classifier. 87% is pretty good. So guys, with this we come to the end of today's session. If you have any doubts or queries regarding our session today, please leave them in the comment section and we'll get back to you at the earliest. Thank you so much for watching this video. Have a great day.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!